The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so today we have a new topic, and we're going to start to learn about vector fields and line integrals. So last week we've been doing double integrals. For today we just forget all of that, but don't actually forget it, put it away in a corner of your mind. It's going to come back next week. But what we do today, we're going to do line integrals, and these are completely different things. So it helps actually if you don't think of double integrals at all while doing line integrals. So anyway, let's start with vector fields. So what's a vector field? Well, a vector field is something that's of a form, well, it's a vector, but where m and n, the components, actually depend on x and y, on the point where you are. So they are functions of x and y. So what that means concretely is that at every point in the plane, you have a vector. Okay, so in a cornfield, everywhere you have corn. In a vector field, everywhere you have a vector. That's how it works. Okay, so a good example of a vector field, I don't know if you've seen these maps that show the wind, but so here's some cool images done by NASA. So actually that's a picture of the wind patterns off the coast of California with Santa Ana winds, in case you're wondering what's been going on recently. So you have all of these vectors that show you the velocity of the air basically at every point. I mean, of course, you don't draw it at every point because, if you draw a vector at absolutely all the points of a plane, then you just fill up everything and you wouldn't see anything. So you just, choose points and you draw the vectors at those points. So here's another cool image of, it's upside down. That's a hurricane off the coast of Mexico with the winds spiraling around the hurricane. So anyway, it's kind of hard to see. You don't really see all the vectors. Actually, I guess the autofocus is having trouble with it. Yeah, it can't really do it. So I guess I'll go back to the previous one. But, OK. So anyway, a vector field is something where at each point, in the plane, we have a vector f that depends on x and y. So this occurs in real life when you look at velocity fields in a fluid. For example, the wind, that's what these pictures show. At every point, you have a velocity of a fluid that's moving. Another example is force fields. So now, force fields are not something out of Star Wars, okay? It's just, if you look at gravitational attraction, you know that if you have a mass somewhere, well, it will be attracted to fall down because of a gravity field of the Earth, which means that at every point, you have a vector that's pointing down. And same thing in space, you have the gravitational field of planets, stars, and so on. So that's also an example of a vector field because wherever you go, you would have that vector, and what it is depends on where you are. So the examples from the real world are things like velocity in a fluid or force field where you have a force that depends on the point where you are. So we're going to try to study vector fields mathematically, so we won't really care what they are most of the time. But as we'll explore with them, define quantities and so on, we'll very often use these motivations to justify why we would care about certain quantities. Okay, so the first thing we have to figure out is how do we draw a vector field? So, how do you generate a plot like that? So let's practice drawing a few vector fields. Well, let's start with, let's say our very first vector field will be just 2i plus j. So it's kind of a silly vector field because it doesn't actually depend on x and y. So that means it's the same vector everywhere. Okay, so I take a picture of the plane, and I take the vector 2, 1. I guess it points in that direction. It's 2 units to the right, 1 up. And I just put that vector everywhere. Okay, so, you just put it at a few points all over the place. And when you think you have enough so that you understand what's going on, then you stop. So here probably we don't need that many. I mean, here I think we get the picture. Okay. So everywhere we have a vector 2, 1. Now let's try to look at slightly more interesting examples. Okay, let's say I give you the vector field x times I hat. Okay, so there's no j component. So how would you draw that? Maybe I don't need that much. Well, so first of all, we know that this guy is only in the I direction, so it's always horizontal. Right? It doesn't have a j component, so everywhere it will be a horizontal vector. Now the question is, how long is it? Well, how long it is depends on x. So for example, if x is 0, then this will be actually the 0 vector. So x is 0, that's here. See, on the y-axis, maybe I should take a different color. So if I'm on the y-axis, I actually have the 0 vector. Now, if x becomes positive small, then I will have actually a small positive multiple of I, so I will be going a little bit to the right. And then if I increase x, then this guy becomes larger, so I get a longer vector to the right. If x is negative, then my vector field points to the left instead. So it looks something like that. Okay. Any questions about that picture? No. Okay, so usually we're not going to try to have, very accurate, we won't actually take time to plot a vector field very carefully. I mean, if we need to, computers can do it for us. But it's useful to have an idea of what the vector field does roughly, whether it's getting larger and larger, in what direction it's pointing, what are the general features. So just to do a couple more. And actually, you'll see very quickly that the examples I take in lecture are pretty much always the same ones. So, we'll be playing a lot with these particular vector fields, just because they are good examples. So let's say I give you xi plus yj. So that one has an interesting geometric significance. If I take a point xy, so there I want to take the vector xy. How do I do that? Well, it's the same as the vector from the origin to this point. So I take this vector and I copy it so that it starts at my given point. Okay, so it looks like that. And same thing at every point. Oops. So it's a vector field that's pointing radially away from the origin, and its magnitude increases with distance from the origin. Okay, so you don't have to draw, as many as me. But so the idea is this vector field everywhere points away from the origin, and its magnitude is equal to the distance from the origin. So, if these were, for example, velocity fields, well, that would tell you, you would see visually what's happening to your fluid. Like here, maybe you have a source at the origin that's spewing fluid out, and it's flowing all the way away from that. Okay, let's do just a last one. Let's say I give you minus y comma x. What does that look like? That's an interesting one, actually. It's a nice one. So let's see. So let's say that I have a point xy here. Okay, so this vector here is x comma y, but the vector I want is negative y comma x. So what does that look like compared to? Yeah, it's perpendicular to the position to this vector. Okay, if I rotate this vector, so let me maybe draw a picture on the side. If I take the vector xy, then the vector with components negative y and x is going to be like this. It's the vector that I get by rotating by 90 degrees counterclockwise. And of course, I don't want to put that vector at the origin. I want to put it at the point xy. So in fact, what I will draw is something like this. Okay, and similarly here, it would be like that, like that. And if I'm closer to the origin, then it looks a bit the same, but it's shorter. Okay, and at the origin, it's 0. And when I'm further away, it becomes even larger. So see, this vector field, if it was the motion of a fluid, it would correspond to a fluid that's just going around the origin in circles, rotating at uniform speed. Okay, so this is actually the velocity field for uniform rotation. And if you figure out, how long does it take for a particle of fluid to go all the way around, well, that will be actually 2 pi, because the length of a circle is 2 pi times the radius. So that's actually at unit angular velocity. 1 radian per second, or per unit time. Okay, so that's why this guy comes up quite a lot in real life. Okay, and you can imagine lots of variations on these. Of course, you can also imagine vector fields given by much more complicated formulas, and then you'll have a hard time drawing them. So maybe you'll use a computer, or maybe you'll just give up and just do whatever calculation you have to do without trying to visualize the vector field. But if you have a nice, simple one, then it's worth doing it, because sometimes it will give you insight about what we're going to compute next. Okay, any questions first about these pictures? No? Okay. Oh, yes. Sorry? Y and, you're asking if it should be Y and, so Y comma negative X, I think would be the other way around. See, for example, if I'm at this point, then Y is positive and X is 0. So if I take Y negative X, I get a positive first component and 0 for the second one. So Y comma negative X would be a rotation at unit speed in the opposite direction. Okay? So yeah, and there's a lot of tweaks you can do to it. But so if you flip the signs, you get rotation in the other direction. How do I know? How do I know that it's at unit angular velocity? Well, that's because if my angular velocity is 1, then that means that the speed, the actual speed, is equal to the distance from the origin, right? Because the length, the arc length on a circle of a certain radius is equal to the radius times the angle. So if the angle varies at rate 1, then I travel at speed equal to the radius, and that's what I do here. The length of this vector is equal to the distance from the origin. I mean, it's not obvious on the picture, but really the vector that I put here is the same as this vector rotated, so it has the same length. So that's why the angular velocity is 1. It doesn't really matter much anyway, but. Okay. So now what are we going to do with vector fields? Well, we're going to do a lot of things, but let's start somewhere. So one thing you might want to do with a vector field is, so I'm going to think for now of the situation where we have a force, okay? So if you have a force exerted on a particle, and that particle moves on some trajectory, then probably you've seen in physics that the work done by the force corresponds to the force dot product with the displacement vector, how much you have moved your particle. And of course, if you do just a straight line trajectory, or if the force is constant, that works well. But if you're moving on a complicated trajectory and the force keeps changing, then actually you want to integrate that over time. So, okay, so we're going to, the first thing we'll do is learn how to compute the work done by a vector field. And mathematically, that's called a line integral. Okay, so physically, remember, the work done by a force is the force times the distance. And more precisely, it's actually the dot product between the force as a vector and the displacement vector for a small motion. So say that your point is moving from here to here. You have the displacement delta r, that's just the change in the position vector. Okay, that's the vector from the old position to the new position. And then you have your force that's being exerted, and you do the dot product between them. And that will give you the work of the force during this motion. And the physical significance of this, well, the work tells you basically how much energy you have to provide to actually perform this motion. Okay, just in case you haven't seen this in 801 yet. I'm hoping all of you have heard about work somewhere. But in case it's completely mysterious, that's the amount of energy you have to provide. Sorry, actually, no, that's the amount of energy provided by the force. Sorry. Right, so if the force goes along the motion, it actually pushes the particle, it provides energy to it to do that motion. And conversely, if you're trying to go against the force, then you have to provide energy to the particle to be able to do that. So in particular, the work, if this is the only force that's taking place, then the work will be the variation in kinetic energy of the particle along the motion. So now that's a good description for a small motion, but let's say that my particle is not just doing that, but it's doing something complicated. And my force keeps changing, so somehow maybe I have a different force at every point. So then I want to find the total work done along the motion. Well, what I have to do is I have to cut my trajectory into these little pieces, and for each of them I have a vector along the trajectory. I have the force, I do the dot product, and I sum them together. And of course, the actual answer, well, to get the actual answer, I should actually cut into smaller and smaller pieces and sum all of the small contributions to work. So in fact, it's going to be an integral. Okay, so along some trajectory, let's call C the trajectory for curve. You know, it's some curve. And here, the work adds up to an integral which, well, we write this using the notation integral along C of f dot dr. Okay, so we have to decode this notation. So one way to decode this is to say it's a limit as we cut into smaller and smaller pieces of the sum over each piece of the trajectory of the force at the given point dot product with that small vector along the trajectory. And, well, that's not how we're going to compute it. You know, to compute it, we do things differently. So how can we actually compute it? Well, what we can do is say that actually we are cutting things into small time intervals. So the way that we split our trajectory is we just take a picture every, say, millisecond. So every millisecond we have a new position. And the motion, the amount by which you have moved during each small time interval is basically the velocity vector times the amount of time. So, in fact, let me just rewrite this as you do the dot product between the force and how much you have moved. Well, if I just rewrite it this way, nothing's happened, but what this thing is actually is the velocity vector. dr dt. So what I'm trying to say is that I can actually compute my integral by integrating f dot product with dr dt over time, from time, whatever the initial time to whatever the final time is. I integrate f dot product velocity dt. And of course, I mean, here when I say f, I mean f at the point on the trajectory at time t. Right? This guy depends on x and y, therefore it depends on t. Okay, I see a lot of confused faces. So let's do an example. And then I will ask you. Oh, okay. So now, yes, that would be probably, yeah, so here I need to put a limit as delta t tends to 0. I cut my trajectory into smaller and smaller time intervals. For each time interval, I have a small motion, which is essentially velocity times delta t, and then I dot that with a force, and I sum them. Okay, so let's do an example. Let's say that we want to find the work of this force. So I guess that's the last example that we had. Okay, so it's a force field that tries to make everything rotate somehow. Your force points along these circles. And let's say that our trajectory, our particle is moving along the parametric curve, x equals t, y equals t squared, for t going from 0 to 1. Okay, so what that looks like, well, maybe I should draw a new picture. So our vector field oh, well, whatever. And our trajectory, if you try to plot this, well, you see y is actually x squared. So it's a piece of parabola that goes from the origin to 1, 1. Okay, that's what our curve looks like. Okay, so we're trying to find the work done by our force along this trajectory. I should point out, I mean, if you're asking me, how did you get this? That's actually the wrong question. I didn't, this is all part of the data. I have a force, and I have a trajectory, and I want to find what's the work done along that trajectory. These two guys I can choose completely independently of each other. Okay. So the integral along C of f dot dr will be, well, it's the integral from time 0 to time 1 of f dot the velocity vector dr dt times dt. So that will be the integral from 0 to 1 of, okay, let's try to figure it out. So what is f? F at a point xy is minus y comma x. But if I take the point where I am at time t, then x is t and y is t squared. Okay, so here I plug x equals t, y equals t squared. That will give me negative t squared and t. Okay, so here I will put negative t squared t dot product. What is the velocity vector? Well, dx dt is just 1. dy dt is 2t. So the velocity vector is 1 and 2t dt. Okay? So now we have to continue calculation. We get integral from 0 to 1 of what is this dot product? Well, it's negative t squared plus 2t squared. I get t squared. Well, maybe I'll write it. Negative t squared plus 2t squared dt. That ends up being integral from 0 to 1 of t squared dt, which you all know how to integrate and get 1/3. Okay? So that's the work done by the force along this curve. Yes?
Did you get the negative t squared plus 2t squared there at the end?
Well, I got it by just taking the dot product between the force and the velocity. Okay? Sorry, that's, in case you're wondering, things go like this. Okay, any questions on how we did this calculation? No? Yes? Why can't you just do f dot dr? Well, soon we'll be able to. We don't know yet what dr means or how to use it as a symbol. Okay? Because, we haven't said yet. I mean, see, this is a d vector r. That's kind of a strange thing to have. And certainly r is not a usual variable. I mean, we have to be careful about, what are the rules? What does this symbol mean? So, I mean, we're going to see that right now. And then we can do it actually in a slightly more efficient way. But you can't just use, I mean, r is not a scalar quantity. R is a position vector, right? So you can't integrate f with respect to r. We don't know how to do that. Okay. So, oh, yes, sorry. I can't see people up there because of the spotlights, but yes. If I were to do, sorry, I still can't hear you, sorry. Okay, so question is, if I took a different trajectory from the origin to that point 1, 1, what would happen? Well, the answer is I would get something different. Okay, so for example, let me try to convince you of that. For example, say that I chose to instead go like this and then around like that. Then, first I wouldn't do any work because here the force is perpendicular to my motion, and then I would be going against the force all the way around, so I should get something that's negative. Okay, even if you don't see that, just, accept at face value what I'm going to say now. The value of a line integral in general depends on how we got from point A to point B. And that's why we have to compute it by using the parametric equation for the curve. It really depends on what curve you choose. Okay. Any other questions? Oh, yes. So yes, what happens when the force inflects the trajectory? Well, then actually you'd have to solve a differential equation telling you how the particle moves to find what the trajectory is. So that's something that would, be a very useful topic, and that's probably more like what you will do in 1803, although maybe you actually know how to do it in this case. So what we're trying to develop here is a method to figure out if we know what the trajectory is, what the work will be. It doesn't tell us what the trajectory will be. But of course, we could also find that. But here, see, I'm not assuming, for example, that the particle is moving just based on that force. Maybe actually I'm here to hold it in my hand and force it to go where it's going. Or maybe there's some rail that's taking it on that trajectory or whatever. So I can really do it along any trajectory. And if I wanted to, if I knew that it's the case, then I could try to find the trajectory based on what the force is. But that's not what we are doing here. Okay. So next. Okay, so let's try to make sense. I mean, you asked a while ago, just a few minutes ago, what can we do directly with dr? So dr, see, becomes somehow a vector. I mean, when I replace it by dr dt times dt, it becomes something that's a vector, but with a dt next to it. So in fact, well, it's not really new, but let's see another way to do it. Let's say that our force has components m and n. I claim that we can write symbolically vector dr stands for, it's a vector whose components are dx and dy. Okay. So now that's a strange kind of vector. I mean, it's not a real vector, of course, but as a notation, it's a pretty good notation because it tells us that f dot dr is m dx plus n dy. And so, in fact, we'll very often write, instead of f dot dr, line integral along C, we'll write the line integral along C of m dx plus n dy. And so in this language, of course, what we're integrating now, rather than a vector field, becomes a differential. But you should think of the two as being pretty much the same thing, right? It's like when you compare the gradient of a function and its differential. They are different notations, but they have the same content. Okay, so now there still remains the question, how do we compute this kind of integral? Because it's more subtle than the notation suggests, right? Because m and n both depend on x and y. And if you just integrate it with respect to x, you'd be left with y's in there, and you don't want to be left with y's. You want a number at the end. And see, the catch is along the curve, x and y are actually related to each other. So whenever we write this, we have two variables, x and y, but in fact, along the curve C, we have only one parameter. Could be x, could be y, could be time, whatever you want. But we have to actually express everything in terms of that one parameter. And then we get a usual single variable integral. Okay, so how do we evaluate things in this language? Well, we do it by substituting a parameter into everything. Okay, so the method to evaluate is to express x and y in terms of a single variable. And then substitute that variable. Okay, so let's, for example, redo the one we had up there, just using these new notations. You'll see it's the same calculation, but with different notations. So in that example that we had, our vector field f was negative y comma x. So what we're integrating is negative y dx plus x dy. Okay? And see, if we have just this, we don't know how to integrate that. I mean, well, you could try to come up with like a negative xy or something like that, but that actually doesn't make sense. It doesn't work. So what we'll do is we'll actually have to express everything in terms of a same variable, because it's a single integral. We should have only one variable. And what that variable will be, well, if we just do it the same way, that would just be t. So how do we express everything in terms of t? Well, we use the parametric equation. We know that x is t and y is t squared. Okay? So we know what to do with these two guys. What about dx and dy? Well, it's easy. We just differentiate. Dx becomes dt. Dy becomes 2t dt. I'm just saying in a different language what I said over there with dx dt equals 1, dy dt equals 2t. It's the same thing, but written slightly differently. So now, I'm going to do it again. I'm going to switch from one board to the next one. My integral becomes the integral over c of negative y is minus t squared dt plus x is t times dy is 2t dt. Okay? And now that I have only t left, it's fine to say, oh, I have a usual single variable integral over a variable t that goes from 0 to 1. So now I can say, yes, this is the integral from 0 to 1 of that stuff. Well, I can simplify a bit, becomes just t squared dt, and I can compute it. I have negative t squared, and then I have plus 2t squared. So I end up with positive t squared. Okay, it's the same as up there. Okay, any questions? Yes? When you do dy, so what is dy? Dy is the derivative of y, it's the differential of y. Y is t squared, so I get 2t dt, okay? So I plug dt for dx, I plug 2t dt for dy, and so on. Okay, and that's the general method. So if you are given a curve, then you first have to figure out how do you express x and y in terms of the same thing. And you get to choose, in general, what parameter we use. Okay, you choose to parameterize your curve in whatever way you want. So the note that I want to make is that this line integral depends on the trajectory c, but not on the parameterization. Okay, so you can choose whichever variable you want. So for example, what you could do is, when you know that you have that trajectory, you could also choose to parameterize it as x equals, say, I don't know, x equals sine theta, and y equals sine square theta, because y is x squared, where theta goes from 0 to pi over 2. And then you could get dx and dy in terms of d theta, And you'd be able to do it with a lot of trig, and you would get the same answer. So that would be a harder way to get the same thing. Okay, so what you should do in practice is use the most reasonable way to parameterize your curve. If you know that here you have a piece of parabola y equals x squared, there's no way you will put sine and sine squared. You could set, x equals t, y equals t squared is very reasonable. You can even take a small shortcut and say that your variable will be just x. So that means x, you just keep it as it is. And then when you have y, you set y equals x squared, dy equals 2x dx, and then you have an integral over x. That works. Okay, so this one is not practical. But you get to choose. Okay. So now let me tell you a bit more about the geometry. Okay. So we've said, here's how we compute it in general. And that's the general method for computing a line integral for work. You can always do this. Try to find a parameter, the simplest one, express everything in terms of that variable, and then you have an integral to compute. But sometimes you can actually save a lot of work by just thinking geometrically about what this all does. Okay, so let me tell you about the geometric approach. So one thing I want to remind you of first is, what is this vector dr? Well, what is vector delta r? If I take a very small piece of a trajectory, then my vector delta r will be tangent to the trajectory. So it will be going in the same direction as the unit tangent vector t. And what is its length? Well, its length is the arc length along the trajectory, which is what we called delta s. Remember, s was distance along the trajectory. So we can write vector dr. So we said it's dx, dy, but that's also t times ds. It's a vector whose direction is tangent to the curve and whose length element is actually the arc length element. If you don't like this notation, think about divide everything by dt. Then what we're saying is dr dt, that's the velocity vector. While in coordinates, the velocity vector is dx dt, dy dt. But more geometrically, the direction of a velocity vector is tangent to the trajectory, and its magnitude is speed, ds dt. Okay, so that's really the same thing. Okay, so if I say this, that means that my line integral of f dot dr, well, I said I can write it as integral of m dx plus n dy. That's what I will do if I want to actually compute it by computing the integral. But if instead I want to think about it geometrically, I could rewrite it as f dot t ds. Okay, so now you can think of this, f dot t is a scalar quantity. It's the tangent component of my force. So I take my force and I project it to the tangent direction to the trajectory. And then I integrate that along the curve. It's still the same thing. And sometimes it's easier to do it this way. So here's an example. Let's say So, this is bound to be easier only when the field and the curve are relatively simple and have a geometric relation to each other. If I give you an evil formula with, x cubed plus y to the fifth or whatever, there's very little chance that you will be able to simplify it that way. But let's say that I'm doing, say, my trajectory is just a circle of radius a centered at the origin. Let's say I'm doing that counterclockwise. And let's say that my vector field is xi plus yj. Okay, so what does that look like? Well, so my trajectory is just this circle. My vector field, remember xi plus yj, that's the one that's pointing radially from the origin. So hopefully, if you have good physics intuition here, you already know what the work is going to be. Right? It's going to be 0, because the force is perpendicular to the motion. Well, now we can say it directly by saying, well, if we take any point of a circle, so if you have any point of a circle, then the tangent vector to the circle will be tangent, well, it's tangent to the circle, so that means it's perpendicular to the radial direction, while the force is pointing in the radial direction, so you have a right angle between them. So f is perpendicular to t, so f dot t is 0, and the line integral of f dot t ds is just 0. See, that's much easier than writing, well, this is integral of x dx plus y dy. What do? Well, we set x equals a cosine theta, y equals a sine theta. We get a bunch of trig things. Oh, it cancels out to 0. It's not much harder, but we saved time by not even thinking about how to parameterize things. Let's just do a last one. That was the first one. Let's say now that I take the same curve, C, but now my vector field is the one that rotates. Negative yi plus xj. Okay, so that means along my circle, the tangent vector goes like this, and my vector field is also going around. So in fact, at this point, the vector field will also be going in the same direction. Okay? So now, f is actually parallel to the tangent direction. So that means that the dot product f dot t, remember that's the component of f in this direction, that will be the same as the length of f. Right? But what's the length of f on this circle if this radius is a? It's just going to be a. That's what we said earlier about this vector field. So at every point, this dot product is a. Now we know how to integrate that quite quickly. Because that becomes the integral of a ds, but a is a constant, so we can take it out. And now what do we get when we integrate ds along C? Well, we should get the total length of the curve, right? If we sum all the little pieces of arc length. But we know that the length of a circle of radius a is 2 pi a, so we get 2 pi a squared. If we were to compute that by hand, well, what would we do? We'd set, so we would be computing integral of minus y dx plus x dy. We'd probably set, since we're on a circle, x equals a cos theta. y equals a sine theta for theta between 0 and 2 pi. So then we would get dx and dy out of these. So y is a sine theta. Dx is negative a sine theta d theta, if you differentiate a cosine, plus a cos theta d theta. Well, you'll just end up with integral from 0 to 2 pi of a squared times sine square theta plus cosine square theta d theta. That becomes just 1, and you get the same answer. It took about the same amount of time because I did this one rushing very quickly, okay? But normally it takes about, at least twice the amount of time to do it with a calculation. So that tells you sometimes it's worth thinking geometrically.